there's a way to bargain in there. All right. As I said today, we're going to compare what we did yesterday and blend it with what we know of the normal distribution. As I said, most of this class is going to be predicated around probabilities, statistics. We're going to take what we've done with experimental design. We're going to look at actual data from experiments, and then we are going to crunch it. Today we're just going to look at some data sets. I want to get back to mean and standard deviation. Remember, your normal distribution is for continuous data. I talked to you guys about continuous data a little bit earlier. And today we're going to look at discrete data, but we're going to compare it against the continuous model of the normal distribution. So you're going to see some things happen. You'll see some similarities, and you'll also see some differences. Okay? The mean value of the random variable, like I said, we're talking about discrete random variables today. Mean value is denoted by this symbol. That is called mu x. That is the Greek symbol mu. That's how I write it. So mu x, we're talking about the expected value. In these problems, the mean means expected value. And you guys have already seen expected value a couple of times. Standard deviation of the random variable is denoted by sigma x, and it'll be written as a subscript. Both these will be written as a subscript. So that's the mean standard deviation. This should make sense to you. A reminder, because we haven't covered it for a while. When your standard deviation is small, your data is grouped close together. When your standard deviation is large, your data is spread out, has greater variability. Okay? And again, that's kind of a bit of summary. Mu and sigma, that's what we call them. They're just the Greek letters. Okay? Okay to go to the first example? There's your 68, 95, 99 chart. Just to review, you've seen it before. I told you to memorize it. You should have it. This is the normal curve. It's also the empirical rule. Empirical rule means if our data is well approximated by the normal curve, we can apply the properties of the normal curve. Okay? And that's, again, review from the previous chapter, chapter 4, I believe. Okay? A couple examples real quick. It should make sense to you. These are two normal distributions. In this case, they have the same standard deviation. They have different means. Does that make sense to you? They have the same variability, same standard deviation, different means. The mean is always at the center. So this one's mean is here, and this one's mean is there. This one, two normal distributions, different size standard deviations, same mean. And again, the area under those curves is still represented as 100% or 1 when we talk about probabilities. Half your data is on the right-hand side, half the data is on the left-hand side. The smaller, flatter one has greater variability, has a bigger spread of the data. And again, that should make sense with what we know. Okay? And that's just about review. All right. Mean of discrete random variables denoted by mu x. You've seen this. We've already covered it 2 or 3 times. Once again, that is expected value. You should recognize all the symbols there. This is review. It should be. The first time you saw this formula for expected value was back when I did the gambling game. And it's going to cost you $50 to play the game. Do you want to play the game or not? And then how long am I going to go to prison? Right? That was expected value. If you can think back to that example, that's exactly what we did. Took the value and multiplied it by the probability, then we summed them all up. And it should make sense. And for those of you guys who are looking just at that 3.5, you guys averaged them. That's because all the probabilities are the same. Okay? Here's our data set. Represents the number of defective tires on randomly selected automobiles. Should make sense to you that it's going to fit in one of these categories. It should make sense to you that in this case, either a tire is defective or it is not defective. We can't have a half defective tire. If it's half defective, it is defective. It doesn't work. Okay? So again, this is the idea of discrete random variables. In this case, this is a car better than yesterday-ish, I guess. If we're looking at defective tires, we're looking at some bad cars in this class. Yesterday was a number of major defects. Yeah. This one's 54% of the time we don't have any tires defective. 16% of the time we got one tire defective, 6% of the time 2, 4% of the time 3, and 20% of the time all 4 tires are defective. Yeah, don't get your tires from here. Do you agree that, roughly speaking, a quick histogram, 54%, 16%, 06%, 4%, and then up there at 20%, roughly speaking, that's our histogram? What would we describe that histogram as? Bimodal. Definitely not normal. Probably bimodal there would be our best descriptions. Okay? So we don't have a normal distribution here. Do you guys agree with that? Okay? But what we're going to do in just a second is we're going to apply the normal distribution. So I'll apply standard deviation to it. First off, calculate mu x. Mu x is written as the mean value of x. This is the expected value. You guys can do this right now on your own. And it should make sense to you that expected value is going to be the sum of all of them. It's going to be x times the probability of x. That's our formula. I just wrote it. Pretty easy to do on this problem. 0 times 0.54, 1 times 0.16, 2 times 0.06, 3 times 0.04, and 4 times 0.2. And then what are you going to do to all those values? Add them up, and that'll get you your expected value. Okay? Now, this is not a very big data set, so it's up to you. You could do this in list 1 and list 2, if you'd like. Can you make that list 1 and that list 2? And then make list 3 list 1 times list 2 and just sum up list 3? Does that make sense? Okay. So I want you guys to go ahead and calculate that expected value right now. Yeah. Yes, please. Is everybody okay with the 1.2 there? Any questions or clarifications on how I got it? All right. So we know that the mean is 1.2, and that's our expected value. In this case, according to this data in this problem, we'd expect on average 1.2 defective tires. Does that make sense? Now, 1.2, and in terms of our distribution, you guys agree that 1.2 is somewhere like about in that part of that histogram? Do you also hopefully agree with me that 1.2 is not a good measure of what's happening with this data? Because most of the time, either no tires are going to be defective or all 4 are. So 1.2 tires defective isn't really a good guesstimate or a good estimate. Does that make sense? Okay. So 1.2, that's our mean value. What else have we got? Next up, calculate the standard deviation. Standard deviation is given to you on your formula sheet. The standard deviation is this thing right here. Sigma squared x, and that's what's given to you, is the sum of x minus mu squared times the probability of x. That's what's given to you on your formula sheet. Hopefully you'll agree with me that that's the variance. To get from the variance to the standard deviation, what do you do to that answer? Square root. And standard deviation is just sigma by itself. So sigma x. Lesser. Personally, I'm going to do this one in my calc. I don't want to do it by hand, but if you wanted to do it by hand, it would be this. What did we say our expected value or our average was? 1.2. Okay? So I'm going to have to go 0 minus 1.2 squared times 0.54. 1 minus 1.2 squared times 0.16. 2 minus 1.2 squared times 0.06. 3 minus 1.2 squared times 0.04. And 4 minus 1.2 squared times 0.20. Now, statistically, that's what's happening. Here's the deal that I want to see the connections in terms of mental thinking. Do you agree that's telling us how far away we are from average? 0 minus 1.2. That's how far away from average we are. And it's going to happen 54% of the time. So 54% of the time, I'm that far away. 16% of the time, I'm that far away. 6% of the time, I'm that far away. And 4% of the time, I'm that far away. And 20% of the time, I'm that far away. Remember, standard deviations and variance is telling us how far away we are from average, on average, if that kind of makes sense. Okay? So, we're going to go ahead and calculate that. Personally, again, you can do it by hand if you'd like. You're going to have to sum those things up. I'm going to do it in my calc. And I have those in list 1 and list 2 already. Oops, that doesn't matter. I cleared out list 3. I had something in list 3. That's where I found my expected value. But I want list 3 to equal my x value, which is in list 1, minus what? 1.2. And what do I need to do with that? Square it. And then what do I need to do? Multiply it by its probability. L2. Okay? There you go. Again, we could have done that by hand. I just think it's easier to work in the calculator. And now what do I need to do with that? I need to sum it, and that will give me my variance, give my standard deviation. What do I need to do from that? Square root of the question. How do we sum it? Exit out of this? Well, sum it is what happens when you actually press the clip. Then you start going back down.
So funny.
How do you sum it? You go second stat, which gets you to the list. You go over to math, and I believe it's option number 5. And we want to sum list 3. 2.52, that is your variance. 2.52 is your variance. To get your standard deviation, you square root the variance. And that is your standard deviation. What do we got? 1.587? 1.875. Yep. 1.5875. Quick point about 4 decimal places, people. Round to 4 decimal places. Okay? 0.00 does not count as 2 decimal places. I need 4 decimal places after that. Okay?
Significant digits.
Sig figs, not decimals. These are just placeholders. Okay? Are we okay with that standard deviation then? What's that? List 3 was this. I made it. I just made list 3 equal to list 1 minus 1.2. Close the parentheses, squared it, and then I multiplied it by list 2. Yeah. But you don't need that list 4. Exit out of that whole thing. Now it's.
was just
go.
gonna.
All right. Everybody okay with this so far? Do we agree that we have the mean of 1.2 and that standard deviation? And again, this data is discrete. That means it's 0, 1, 2, 3, or 4 defective tires. Now we need to know, what is the probability that x exceeds the mean value? The probability that x exceeds the mean value. Remember, we don't have partial pieces in this problem. It's a tongue twister. I look at this as almost a number line. That's what kind of helps me visualize this stuff. So 1.2, if that's 0, that's 1, that's 2, that's 3, that's 4. 1.2 is roughly about, say, there on my number line. Are we okay with that? Now, 1.2 is my mean. I want the probability that x exceeds the mean value. That means bigger than the mean value. Does everybody agree with what that statement says? Because this is where students make their mistakes. Well, let's see. Bigger than the mean value, since 1.2 is in this level, they tend to count that. No, that's the probability that there's one defective tire. 1.2 is more than one defective tire. So things that are greater than 1.2 are the 2, the 3, and the 4. So the probability that x is greater than the mean value is going to be 0.06 plus 0.04 plus 0.2. Yeah, it's going to come out to be 0.3. Questions on that? That one's kind of easy. Next one. I think it's the same data set. Part D. What is the probability that x is within one standard deviation of the mean? Okay? Probability that x is within one standard deviation. Our mean is still 1.2. Our standard deviation, what was it? 1.5, 875. Okay. Our mean is still here at 1.2. I need to know the probability that x is within. That means captured by. Do we agree with that? So I need to figure out my distances. Think about this the same way that we talked about calculating outliers. It's almost easier here. I need to get one standard deviation above the mean to find that breakpoint. So 1.2 plus 1.5875 gets me, I'm just going to write kind of one standard deviation above. Does that kind of make sense? And to get one standard deviation below, it's going to be 1.2 minus my standard deviation, which is going to get me to my breakpoint. Just like, remember, we did breakpoints for outliers. This is going to be my breakpoint for standard deviation. So 1.2 plus 1.5875, what do we got? 2.7875? Is that right? So 2.7875. So for me, I'm looking at the number line again. 2.7875 gets me to about here. It doesn't have to be perfect, but that just helps me make a visual. One standard deviation below, that's going to get me to what? Negative, I don't know what that one is. Negative 0.3875. And so that's going to get me below 0. Agree? And so again, I just need to get rough estimates because this helps me understand what's happening. Within one standard deviation is everything that's captured within it. Most students agree that the 0 is captured within that, right? So that one's going to be 0.54. The 1 is captured within it. Notice that I'm adding these probabilities. These are OR situations. I can have 0 defective tires, or I can have 1 defective tire. That makes sense? That's why I'm adding these things together. Should match what we did in the last chapter. Now what about this 2? Do we count it or we don't count it? That's my question, and that's what's usually confusing for students. Yeah, I know you guys have a 50-50 chance of guessing correctly on this. You either count it or you don't count it. But of course, I want to know why we count it or why we don't count it. What? Can't hear you. Okay. Good. It goes all the way up to 2.7875. Remember, we're talking about discrete random variables here. So my value isn't 2.7875. My values are 0, 1, 2, 3, and 4. 2 is within this range, isn't it? Don't you agree? My range is from negative 0.3875 to positive 2.7875. So that means the things that are captured or within it are the 0, the 1, and the 2. So those are the 3 probabilities that I'm going to add. So I will add the 0.06. I don't know what that sums to. Point what? 0.74? 0.76? Okay. So that's the probability that I'm going to be within 1 standard deviation. Now, if this was normally distributed, how much data should be within 1 standard deviation?
68.
About 68% of the data. Notice that this doesn't match up. That's okay, because when we started this problem, I didn't have a normal distribution anyway. Well, that kind of makes sense then, right? All right, next part. What is the probability that x is more than 2 standard deviations away? Usually after you see the first example, you can see how the rest of it's going to go. Now I want what's outside of 2 standard deviations. So we really got to figure out the breakpoints again. And this time it's going to be 1.2 plus 2 standard deviations and 1.2 minus 2 standard deviations. Do we see how we're getting those breakpoints again? And honestly, in the context of this problem, I don't care about this bottom one because I know it's going to be negative, right? If 1 standard deviation was negative, then 2 standard deviations is definitely going to be negative. And I can only have 0. I can't have -1 type defective, right? So that one, you can calculate if you want, but we don't need it. We do need this top breakpoint, though. What's that one come to be? 3.81. So we got back over here, something? 3.81? No, we got something different? 4.3? 4.3? Do we match now? Okay. And we can calculate that bottom one. I'm not too concerned with it. We're talking probability x is more than 2 standard deviations away. Well, again, here's my 1.2. We're right about there. 1.2. I got to get all the way up to 4.375. That's there. It's off my chart. And then I'm getting negative over here. Probability that x is more than 2 standard deviations away. Do I have any data that's outside of 2 standard deviations in this context? No, so that probability is 0. Okay. Just applying means and standard deviations. I think this is kind of, I think this stuff's kind of easier than the probability problems that you guys did, because you never really know what probability you're supposed to do with probabilities. Probably. Questions? All right, you guys do this one.